The universe, a vast and mysterious expanse, not only houses our solar system, but is also home to billions of other planets. Each one a unique, untold story waiting to be discovered. Among these worlds, could there be one like Earth, where life might take root? With the advancement of technology, following the success of Kepler, the TESS telescope was launched in 2018. With its ability to survey 85% of the sky and focus on nearby bright stars, it has ushered in a new era of searching for planets with Earth-like conditions. TOI 700D, a planet similar in size to Earth and located within the habitable zone of a red dwarf star, could be a strong contender for supporting life. Meanwhile, the planet Teegarden B, with the highest Earth similarity index, is sparking curiosity among scientists about the adaptability of life under extreme conditions. However, not all exoplanets promise life. Some planets, like TRESS 2b and 55 Cancri E, possess extreme conditions that render them into what could be described as death planets. Now, let's embark on a journey to uncover the fascinating secrets of these exoplanets. The first and most essential tool in shaping our understanding of distant planets is Kepler. Launched into orbit on March 7, 2009, Kepler was not just a telescope. It was a massive light-measuring machine designed to observe a single section of the sky continuously for nearly a decade. This method relies on a highly refined physical principle. When a planet passes in front of its parent star, it dims the star's light by a fraction, sometimes as little as 0.01%, equivalent to detecting an ant crossing a car's headlights from a distance of 100 meters. Kepler proved that small, Earth-like rocky planets were not anomalies, but rather the rule across the galaxy. With more than 2,600 confirmed planets, Kepler accomplished its mission, providing undeniable statistical evidence of the commonality of other worlds. We found them, but what exactly are they made of? If Kepler was the hunter searching for numbers. The Transiting Exoplanet Survey satellite, launched on April 18, 2018, took a different approach. TESS doesn't aim to look far. Instead, it focuses on nearby. Bright stars and surveys a wide swath of sky. As of now, TESS has confirmed over 390 exoplanets and created a list of over 6,600 potential candidates. Notably, TESS discovered the TRAPPIST-1 system, shifting the scientific focus from simply proving existence to searching for signs of life. chemical traces in atmospheres by concentrating on brighter, nearer stars within just 200 light years. This strategy is crucial. The closer and brighter the star, the easier it becomes for scientists to use giant ground-based telescopes to take the next step, analyzing the atmospheric properties of exoplanets. With its ability to cover 85% of the sky, TESS scans the entire galaxy in segments, like constructing a grand mosaic. By finding planets orbiting cool, stable dwarf stars, TESS has discovered the first candidates that resemble Earth in size and conditions, located within the Goldilocks zone of their parent stars. The combination of these two missions not only expands our horizons, but also allows us to probe the light passing through planetary atmospheres. A breakthrough that could reveal chemical signs of life known as biosignatures. Among the worlds uncovered, which one truly meets the criteria for fostering life as we understand it? Could the Goldilocks zones hold the answer to the question of our loneliness in the universe? If missions like Kepler and TESS have been successful in identifying thousands of new worlds, then within this vast array of planets, where can we truly find an Earth-like world, where the story of life might begin to unfold? We began searching for worlds not only existing, but also potentially habitable. This is where the concept of the habitable zone, also known as the Goldilocks zone, becomes our guiding principle. The real-world statistics present a shocking and somewhat concerning truth. Most Earth-sized planets discovered orbit red dwarf stars, specifically M-type stars. These stars are the quiet giants, accounting for about 75% of all stars in our galaxy. Since red dwarfs are faint and cold, their Goldilocks zones are pushed close to the star, bringing these planets closer than Mercury is to our Sun. Due to their tight orbits, these Goldilocks worlds are almost certainly tidally locked, with one side perpetually facing the star while the other remains in constant darkness. In their early stages, M-dwarfs often flare up, sending out X-ray and ultraviolet radiation storms that can be 100 to 1,000 times more powerful than our Sun's storms. This high-energy radiation has enough power to strip away the atmospheres of these planets, breaking down water into hydrogen and oxygen and ejecting them into space within just a few million years. Even if life were able to take root on these planets, Could it survive the constant barrage of radiation? One such candidate is the planet TOI 700d. Discovered in January 2020 by NASA's TESS mission. It orbits the quiet red dwarf star about 102 light-years away. The quietness of its host star is a key factor, as it significantly reduces the threat of destructive superstorms compared to other M-dwarf systems. TOI 700d is Earth-sized, about 1.19 times Earth's radius, and is at the perfect distance to complete an orbit in just 37.4 days. It receives about 86% of the energy Earth gets from our Sun. This leads to a theoretical equilibrium temperature that is frozen. However, the actual surface temperature entirely depends on the composition and density of the atmosphere. Early climate models have suggested three main scenarios. A thin, Mars-like atmosphere that would cover the planet in ice. An Earth-like cold atmosphere with potentially frozen oceans. A dense carbon dioxide atmosphere, a primordial atmosphere rich in carbon dioxide. Could create enough greenhouse warming to raise the surface temperature above 0 degrees Celsius, allowing liquid oceans to exist. If the third scenario proves true, TOI 700d might be a warm ocean world. Even though it remains tidally locked, this makes it a prime candidate for atmospheric analyses to search for biosignatures. Another intriguing world is Teegarden B. Orbiting the ultra-cool red dwarf Teegarden, only 12.5 light-years away. Teegarden B holds the highest Earth similarity index, around 0.95. The ESI is a complex measure based on radius, density, escape velocity, and equilibrium temperature, indicating that this planet is almost a perfect physical replica of Earth. This planet has an extremely short orbital period, just about 4.9 days. However, due to its dim star, it receives heat that's very similar to Earth's, leading to an estimated ideal surface temperature. With such a short orbital cycle, Teegarden B is strongly tidally locked. The greatest challenge for life here would be the stability of the horizon zone. One side is perpetually in daylight, and the other side is locked in eternal darkness. The biggest challenge to life here would be surviving the extreme conditions on both the day side and the night side, freezing cold. Life could take the form of microbial communities beneath the surface, like Earth's fossilized life forms. Black sea plants evolved to absorb the faint infrared light of the M star. Organisms moving along the ideal temperature strip of the horizon zone as the planet orbits its star. Detailed analyses of TOI 700D and Teegarden B show that the Goldilocks zone is merely a necessary condition. The true recipe for habitability is the complex interaction between the planet's atmosphere, the parent star's activity, and the adaptability of life itself. We stand at the pinnacle of an extraordinary discovery. Could TOI 700D be a warm ocean world heated by carbon gases? Or is Teegarden B a sanctuary for a resilient biosphere? The exploration of exoplanets has revealed a shocking truth that challenges our imagination. The universe is not limited by the rules we know. Strange worlds exist in the far corners of the universe, where physics and chemistry are turned upside down, and life could evolve in ways we never imagined. One such world is Gliese 1214b, an ocean super-Earth located 48 light-years away. The planet orbits very close to its host star, causing surface temperatures to fluctuate between 120 degrees Celsius and 280 degrees Celsius, a heat so intense that water would instantly evaporate without a thick atmosphere. Under these conditions, water cannot exist in liquid form. Instead, it compresses into strange forms of ice, like Ice Vi or Ice X, which are crystal structures that can exist at temperatures far higher than water's boiling point on Earth. So, what happens under these conditions? Could there be a layer of liquid water between the vaporous atmosphere and the high-pressure ice layer? This raises the intriguing possibility of life in a completely different environment than we ever imagined. Gliese 1214b challenges us to rethink life itself, igniting curiosity about how life could exist in such extreme conditions, unlike anything we've seen on Earth. Wandering planets, which are not bound to any star, introduce a dramatic shift in our understanding of habitable environments. Y0855-0714. A planet with surface temperatures ranging from -48 degrees Celsius to -30 degrees Celsius, is nearly completely isolated from external heat sources. What has kept water stable on this planet despite it not receiving light or heat from a star? The answer may lie in two sustained internal energy sources. The continuous decay of radioactive isotopes like uranium, thorium, and potassium-40 in the planet's core, alongside leftover heat from the planet's formation billions of years ago. These energy sources provide a stable heat supply, enough to sustain a hidden liquid ocean, dark but warm beneath several kilometers of ice. Life on these planets might not rely on photosynthesis like on Earth, but rather on chemosynthesis from hydrothermal vents at the ocean floor. Microorganisms here could endure extreme conditions, completely separated from light and solar energy. This makes us rethink life in the universe and expand our definition of what life can be. These bizarre planets, like Gliese 1214b and Y0855-0714, not only challenge our old definitions of habitable environments, but also make us reconsider the possibility of life existing under physical conditions that were previously unknown. The questions raised about survival in these extreme environments are not just changing the way we understand life, but they are also showing us that the vast universe could harbor creatures unlike anything we've ever known. Life may not only exist where there is liquid water and sunlight, but also in places where these conditions are entirely absent. These discoveries remind us that in the universe, life isn't always what we know. And the search for life may not be just about finding Earth-like conditions. Instead, we may find creatures that have evolved in completely different environments, in places where the conditions we consider essential for life may not even exist. In the relentless quest for life, every discovery of a hostile exoplanet serves as a chilling reminder of nature's cruelty. These worlds are natural laboratories of annihilation, where the laws of physics are twisted, where matter melts, tears apart, and is irradiated down to the atomic level. The death planets are where we witness the greatest brutality of the universe. TESS 2b is one of the most astonishing of these. It is the darkest planet ever discovered, a literal black hole in the fabric of space. TESS 2b absorbs an astounding amount of light from its parent star. Imagine, it's darker than any form of charcoal or synthetic material ever created on Earth. What fuels the endless curiosity about this world is the optical paradox it presents. The planet is tidally locked, rotating so close to its star that its day side reaches a searing 1,000 degrees Celsius. It's like a smoldering ember in eternal darkness. A major physics question arises. What in the atmosphere of TESS 2b could be responsible for such absolute light absorption? Could it be the presence of sodium and potassium gases in an ultra-hot state, broken down to create this incredible light-absorbing ability? Might this phenomenon be replicated by humanity in the future to create super-absorptive materials? Even more dreadful is the atmospheric dynamics at play. Winds on HD 189733b reach speeds several times that of sound and are fast enough to circle Earth in mere hours. These molten glass droplets don't fall straight down, but are swept horizontally by supersonic winds, turning the atmosphere into a massive shredder. What keeps such a dense, silicate-laden atmosphere moving at speeds far beyond the aerodynamic limits we know? Some planets challenge us by transforming matter under unimaginable temperatures and pressures, while others provide us with a rare glimpse into the death of a world. 55 Cancri e was once dubbed the Diamond Planet due to its abnormally high carbon content. It is a tidally locked super-Earth with extreme day and night temperatures. The daytime side of this planet reaches temperatures so high that it melts most metals and silicate materials, creating a liquid magma crust. Meanwhile, the night side still maintains a staggering 1,300 degrees Celsius. Hot enough to melt aluminum, but cold enough to allow carbon vapors to condense and crystallize. If 55 Cancri e melts carbon, K2141b melts its entire rocky surface, creating an entirely new hydrological cycle, the cycle of liquid rock and metal. Nearly the entire surface of K2141b is covered by a vast ocean of molten lava, extending hundreds of kilometers deep. But what truly piques scientific curiosity is its atmosphere. Made up of rock vapors that include sodium and silicon oxide gases. There, the rock vapor condenses and forms a relentless rain of molten rock and metals that falls back into the magma ocean. This planet is constantly being eroded and recreated by its own materials in an unceasing, brutal cycle. WASP-12b is a hot Jupiter spiraling toward its doom. It orbits its parent star at such a close distance that tidal forces have stretched it into an egg-shaped form. Based on the measurable rate of mass loss, we now have a terrifying timeline. WASP-12b will be completely consumed by its parent star in just a few million years. This planet was one of the first exoplanets discovered, but it doesn't orbit a normal star. It orbits PSR 1257 plus 12. a pulsar, the core of a dead star. Spinning rapidly and emitting powerful electromagnetic radiation and gamma rays. The existence of PSR 1257+12 and other pulsar planets has led scientists to propose that these planets formed from the leftover matter after the star's explosion. Much like a phoenix emerging from the ashes of its mother star. But how do the materials that make up these planets withstand the continuous molecular degradation caused by such intense radiation? V391 Pangea B represents a feat of physical resilience. It orbits a dead red giant star. When its parent star expanded into a red giant. It began to engulf the nearby planets. V391 Pangea B was within the range of this destructive expansion. However, through a mechanism not yet fully understood, the planet survived the melting and evaporation of its outer gas layers and stabilized in an orbit far from its parent star. These death worlds reflect the fragility of Earth and the endless complexity of the universe. Mars is currently the focal point of our exploration efforts. Not only because of its proximity, but also because it serves as the first biological laboratory to test our ability to recreate life in a near-deadly environment. Projects like SpaceX's Starship have redefined the concept of space travel, shifting from single missions to a reusable model capable of transporting dozens of people and supplies. The ambitious goal is to establish a base on Mars within the next decade. However, the biggest challenge isn't in the rocket science of launching, but in the ability to withstand radiation during the long journey. Mars lacks a strong magnetic field like Earth's, meaning future inhabitants would face radiation levels many times higher than what we experience here, directly threatening their DNA and significantly increasing the risk of cancer. We have the technology to leave Earth, but we lack the technology to ensure that future generations aboard these ships remain physically and mentally intact. Exploration technology has evolved from merely glimpsing faint lights to the ability to analyze the chemical composition of a world thousands of light years away. The Roman Space Telescope, set to launch in 2027, will utilize coronagraphs to block out starlight and capture direct images of exoplanets. This technology could help us identify geographical features such as oceans or continents on distant planets. The 1967 Outer Space Treaty states that no nation has the right to claim ownership of celestial bodies. However, it doesn't explicitly address the issue of private entities exploiting resources from these bodies. The rise of private companies capable of mining precious metals from asteroids or harvesting water ice on the moon has created a vast legal gray area. One that will require new frameworks to navigate. The principles of SETI, Search for Extraterrestrial Intelligence, have long focused on listening for signals. However, some leading scientists, including the late Stephen Hawking, warned against revealing Earth's location, seeing it as a potential existential risk. The journey of space exploration is a testament to the unrelenting spirit of humanity. It teaches us how fragile life on Earth truly is, and that the greatest challenges we face can only be addressed through cooperation and unity. The journey of exoplanet exploration transcends the boundaries of science, reaching into the deepest questions about our very existence. From identifying potential worlds in the Goldilocks zone, where liquid water could exist, to studying extreme planets with hellish conditions, each discovery reaffirms that the universe is an endless treasure trove of mysteries. Revolutionary tools like Kepler, TESS, and the ambitions of Starship are not just physical instruments. They represent the highest manifestation of human intellect and an unyielding thirst for discovery. However, the most profound value in exploring exoplanets lies not in the worlds we discover, but in the reflection of ourselves. This journey forces us to confront the possibility of survival, adaptation, and, most importantly, the fragility of Earth. Can we secure our existence on this first home before venturing into new homes across space? The future of exoplanet exploration is a blend of science, technology, and moral responsibility. Humanity will continue to seek answers, not only to understand distant worlds, but to shed light on the very origins and limits of our own existence. Enceladus, one of Saturn's small moons, stunned scientists. Data from the Cassini mission revealed extraordinary wonders hidden beneath its thick ice shell. Rather than being an inactive ball of ice, Enceladus erupts from fractures at its south pole, blasting enormous plumes of material straight into space. Analysis of samples collected from these plumes revealed the presence of organic compounds, chemical elements, and ultrafine silica particles, essential ingredients for life. Could there be an active ocean beneath this thick layer of ice? For the first time in human history, we directly accessed and analyzed material from an ocean beyond Earth without the need for a complex landing mission. Enceladus was never intended to be a primary target of the Cassini mission. Yet this unexpected discovery reshaped the way we search for life in the universe. On Saturn's icy moons, the true mystery does not lie on the surface, but deep below it. And Enceladus was the first to open that door. When the Cassini spacecraft flew past Enceladus, it was regarded as nothing more than a small moon, just over 500 kilometers in diameter, classified as a cold, weakly active icy moon. The instruments aboard Cassini began transmitting data that did not match any existing model. At Enceladus's south pole, where scientists expected a quiet, frozen landscape, sensors detected massive plumes of material erupting straight into space. Spectral analysis revealed a powerful, continuous mixture of water, ice, and gas escaping into the vacuum. Enceladus was not gently leaking, it was erupting. Subsequent images confirmed the presence of long parallel fractures stretching hundreds of kilometers across the South Pole. Later named the Tiger Stripes, Cassini measured temperatures along these fractures that were abnormally high. Compared to the rest of the surface, dozens of kelvins warmer than surrounding regions, for a moon as small as Enceladus. Such heat was nearly impossible to explain if it came solely from residual warmth left over from its formation more than 4.5 billion years ago. Then came the numbers that left the scientific community silent. Cassini estimated the eruption rate at between 200 and 250 kilograms of material per second. Airflow large enough to sustain Saturn's E-ring, the faint but expansive ring encircling the gas giant. Particles within the plumes reached speeds exceeding 2,000 kilometers per hour, indicating a powerful energy source pushing material beyond Enceladus's gravitational pull. These plumes were observed repeatedly during multiple flybys, proving that Enceladus is continuously active. The most important question was not the scale of the phenomenon, but its origin. Composition analysis showed that the ejected material did not come from the surface, but from deep within the moon. This meant the ice shell was not a sealed, solid barrier. Beneath it, there had to be a reservoir of liquid water, an ocean. And that ocean was not permanently buried, it was communicating directly with space. During its passages through the plumes, Cassini accomplished something unprecedented. It directly sampled material from an ocean beyond Earth, without landing, without drilling through ice, without ever touching the surface. Defying every prior prediction? What allows such a small moon to sustain intense activity over long periods? Defying every prior prediction? To find the answers, we must go deeper, beneath the ice shell tens of kilometers thick, into a hidden geophysical engine quietly at work. A moon just over 500 kilometers wide. Far smaller than other ocean worlds like Europa or Titan, should have cooled and gone silent billions of years ago. By every classical logic, Enceladus should be a frozen, motionless block of ice, a forgotten relic from the formation of the solar system. Yet the data show the opposite, orbiting Saturn with a period of about 33 hours. Enceladus does not move alone through empty space. It is locked into a 2-to-1 gravitational resonance with Dione, a larger moon on a more distant orbit. Every time Enceladus completes 2 orbits around Saturn, Dione completes exactly 1. This forced synchronization prevents Enceladus's orbit from ever becoming perfectly circular. As Enceladus moves closer to Saturn, the gas giant's immense gravity stretches the moon's entire structure. As it moves farther away, that pull weakens. This cycle of compression and relaxation repeats continuously, tens of thousands of times each year. This is tidal force, not acting on a surface ocean like on Earth, but deep within Enceladus itself. The rocky core of Enceladus is constantly flexed. Microscopic deformations within the silicate rock generate internal friction, and that friction produces heat. This heat does not appear in dramatic explosions, but accumulates slowly and steadily over millions and billions of years. Measurements of the gravitational field, tiny changes in orbital motion, and thermal emission data concentrated at the South Pole all indicate that Enceladus is releasing more energy than can be explained by natural radioactive decay within its rocky core alone. From this evidence, scientists began reconstructing Enceladus as a layered world. At its center lies a silicate-rich rocky core. Surrounding it is a salty liquid ocean. Capped above by an ice shell, roughly 30 to 40 kilometers thick. What is astonishing is not only the existence of this ocean, but its scale. Many models suggest it may be nearly global, rather than confined solely to the polar regions. This ocean does not freeze solid for two reasons. First, heat from the rocky core is continuously transferred into the water through direct contact between rock and ocean. Second, tidal forces prevent the overlying ice shell from ever reaching complete thermal equilibrium. In regions experiencing greater stress, especially near the South Pole, the ice is thinner, allowing heat to escape more easily. This asymmetry explains why geothermal activity is so strongly concentrated in one hemisphere. For decades, science assumed that only sufficiently large celestial bodies could retain heat over long periods of time. Enceladus proves that size is not an absolute determining factor. It does not survive through stability, but through constant tension. Being pulled back and forth between Saturn and Dione is precisely what keeps it alive. If life exists within this ocean, it would be life born of pressure, deformation, and motion, not of quiet equilibrium. Thermal models showed that if Enceladus were to escape its resonance with Dione, its subsurface ocean would freeze over, a relatively short span on cosmic timescales. Geological activity would cease, and the moon would become a dead block of ice, exactly as once assumed. At a deeper level, Enceladus forces us to expand our definition of a living world. It does not require sunlight, a warm surface, or a thick atmosphere. It needs only liquid water, continuous energy, and time. Together, these three elements create an environment that cannot be ignored in any serious discussion of life beyond Earth. But is this ocean isolated? If liquid water were permanently trapped beneath tens of kilometers of ice, direct study would be nearly impossible. Yet, if natural pathways exist that allow the ocean to communicate with the outside world, then Enceladus is not merely an ocean world. It is an open window. beneath ice layers tens, even hundreds of kilometers thick. Liquid water, if it exists at all, has long been considered a secret permanently sealed away. Every exploration scenario runs into the same technical wall. Deep drilling, extreme risk, enormous cost, and a near certain chance of failure. Enceladus shattered that logic in the boldest way imaginable. At Enceladus's south pole, the tiger stripe fractures are not merely geological cracks. They are conduits piercing the ice, directly linking the subsurface ocean to the vacuum of space above. Combined data from high-resolution imaging, thermal maps, and ice structure models reveal that in this region, the ice shell is significantly thinner than the global average. Only a few tens of kilometers, and is subjected to continuous tidal stress. This is precisely what allows the fractures to remain active over long periods, rather than freezing shut like ordinary cracks. The crucial point lies not in the shape of these fractures, but in their consequences. Enceladus's ocean is not isolated. It participates in a dynamic cycle of material exchange. With liquid water, dissolved salts, mineral particles, and gases forced upward through the fractures and released into space. Tiny ice grains, gas molecules, and salts ejected into space carry with them the chemical fingerprints of the environment where they formed. Cassini exploited this reality in an unprecedented way. The spacecraft conducted multiple flybys directly through the plumes at extremely low altitudes, just tens of kilometers above the surface. Instead of drilling or landing, its scientific instruments allowed material from Enceladus to collide with them naturally. For the first time in history, humanity directly sampled an extraterrestrial ocean. Not through inference or theoretical intermediaries. This fundamentally changes how we assess the biological potential of icy worlds. A sealed ocean is a closed system, difficult to access, difficult to verify, and easily sidelined in long-term exploration strategies. In contrast, an ocean that exchanges material with its surroundings becomes a living scientific target. Where chemical and geophysical processes do not merely exist, but leave observable traces. Here, Enceladus sets a new standard. Not all ocean worlds are equal. Scientific value lies not only in the presence of liquid water, but in access to information. Because these plumes exist, if life inhabits Enceladus's ocean, it is not completely hidden. Molecules, complex chemical structures, and even potential biosignatures may already have been, may still be, carried outward with the escaping material. This means that life, if it exists, is not confined solely to the world where it arose, but may leave imprints beyond its own boundaries. At a deeper level, Enceladus forces us to rethink how life interacts with the universe. On Earth, life is largely shielded by an atmosphere and a magnetic field, but on Enceladus, if life exists, it inhabits an environment where the ocean and space are not fully separated. From a strategic perspective, this discovery has completely reordered priorities and future exploration plans. It represents a direct point of contact between humanity and an extraterrestrial environment with exceptionally high biological potential. If material from the ocean has already been exposed, then what exactly does that material contain? Which molecules are being carried up from depths tens of kilometers below the ice? And most importantly, could they hold the first clues to life beyond Earth? When Cassini flew through the streams of material erupting from Enceladus, it did not see life, nor did it capture images of living organisms, but it found an environment where life could exist. In scientific terms, this meant mass spectra, ion analysis, and cold, precise graphs. But behind those numbers lay a story that reshaped how we understand life in the universe. The dominant component in the sampled material was water, not simple vapor from sublimating ice, but water carrying the signature of a true ocean. Cassini detected water mixed with dissolved salts, indicating that this was not newly formed surface water, but water that had existed for a long time, interacting with rock and minerals in a stable environment. This was an ocean that did not appear briefly, but one that had persisted long enough to establish chemical equilibrium. Alongside water were carbon dioxide and methane. These are simple carbon-based molecules. Yet their significance is fundamental. Carbon is the backbone of organic chemistry, and its presence in multiple oxidation states shows that Enceladus is not a chemically poor or static system. On the contrary, it points to an environment where chemical reactions are ongoing, where carbon is redistributed and transformed, a hallmark of potentially biological systems. Cassini also detected nitrogen, an element often overlooked but critically important. Nitrogen is a core component of amino acids, nucleotides, and proteins. In nature, nitrogen does not remain in reactive forms easily without stable chemical cycles. Its presence in the plume suggests that Enceladus's ocean is not merely water and rock, but a chemically complex environment where essential elements are accumulated and cycled. The turning point came with a small molecule of enormous significance, molecular hydrogen. Cassini measured concentrations of hydrogen-2 far higher than could be explained by surface physical processes or radiation-driven ice breakdown. The most plausible source of this molecular hydrogen is hydrothermal reactions between water and rock, similar to the process of serpentization on Earth. When water penetrates hot silicate minerals within a rocky core, chemical reactions occur that release molecular hydrogen. On Earth, hydrogen from deep-sea hydrothermal vents provides energy for ecosystems that do not depend on sunlight. Cassini did not detect organisms, but it did detect free chemical energy, the very thing life can exploit. In biology, energy is not only heat or light, it is the ability to create chemical gradients. Molecular hydrogen, when combined with carbon dioxide, can power reactions that build complex organic compounds. This is the foundation of chemosynthesis, a form of metabolism that existed on Earth very early, even before photosynthesis emerged. The case became even more compelling when Cassini detected nanoscale silica particles in the ejected material. These particles cannot form in cold, static environments. Studies indicate they most likely form when hot. Mineral-rich water interacts with rock at temperatures above 90 degrees Celsius, then cools rapidly as it rises. This provides strong, though indirect, evidence for active hydrothermal systems on the seafloor of Enceladus's ocean. Taken together, the data show that Enceladus possesses the three core ingredients of a potentially habitable environment. Liquid water that is stable and long-lived. A continuous energy source independent of sunlight. And rich chemistry that includes elements and molecules essential for life. None of these conditions is rare on its own. But their coexistence within a single system, on a small moon more than 1 billion kilometers from Earth, has shaken long-held assumptions. Life is no longer tightly bound to planets, to sunlight, or to warm surfaces. It can exist in darkness as long as the chemistry is right. Still, science does not allow for hasty conclusions. Cassini did not detect direct biosignatures. There were no cells, no clear biological structures, no indisputable evidence. What we have is potential, but potential backed by solid experimental data. And in science, potential confirmed by physics and chemistry is often more profound than a single isolated discovery. What Cassini revealed here has become a template for re-evaluating the entire Saturn system. If a small moon like Enceladus can host such a chemically rich and promising environment, then what might other icy worlds around Saturn be hiding? Not just Enceladus, but a cluster of ocean worlds around Saturn. Enceladus does not stand alone. It is merely the first piece of evidence suggesting that the Saturnian system may be a gathering place for multiple ocean worlds, each expressing a different manifestation of the same physical principle. Liquid water can exist in places we once believed to be impossible. The clearest and largest example is Titan, with a diameter of approximately 5,150 kilometers. Titan is larger than the planet Mercury and is the only moon in the solar system with a dense atmosphere, a surface pressure higher than Earth's, and a composition dominated by nitrogen. For decades, Titan has fascinated scientists with its lakes and seas of liquid methane on the surface. A world that resembles early Earth in appearance, but operates under an entirely different chemistry. However, gravity data and rotational oscillations measured by Cassini reveal that Titan's true story lies far deeper beneath its surface. Precise measurements indicate that Titan harbors a subsurface salty ocean buried beneath hundreds of kilometers of ice. This ocean likely contains ammonia, which lowers the freezing point and helps maintain a liquid state over long timescales. If Enceladus represents open oceans where material can escape into space, then Titan represents fully shielded oceans, stable, deep, and isolated from the surface. This opens a thought-provoking possibility. Life, if it exists, may not need to interact with space or the surface to maintain its stability. Titan also demonstrates that the diversity of ocean worlds is not defined by water alone, but by the chemistry surrounding it. On Titan's surface, photochemical reactions produce complex organic molecules. chemical precursors of life. Below, the salty ocean exists in complete darkness. These two environments are largely separated, but if any mechanism of material exchange has occurred between them over Titan's history, the moon could represent one of the most complex natural laboratories the universe has ever produced. Less visually striking than Titan, yet rich in dynamical significance, is Dione. For many years, Dione was regarded as an old, inactive, and unremarkable icy moon. However, data from Cassini show that Dione responds to Saturn's changing magnetic field in a way that can only be explained by the presence of a conductive layer within its interior. The most plausible explanation for this conductive layer is a subsurface salty ocean beneath a thick shell of ice. What makes Dione particularly compelling is not only the possibility of an ocean, but its orbital connection with Enceladus. The two moons maintain a 2-to-1 gravitational resonance, meaning their thermal and energetic histories are not entirely independent. If Enceladus was awakened by tidal forces, then Dione may have experienced, or may still be experiencing, similar cycles of internal activity, even though its surface expression is far more subdued. Dione reminds us that surface silence does not equate to internal emptiness. Then there is Mimas, which directly challenges long-held assumptions. Small, heavily cratered, and long considered a rigid block of ice, almost entirely geophysically dead. There are no plumes, no surface activity, and no obvious thermal anomalies. Precisely for this reason, newly published models from 2023 to 2024 were deeply unsettling. Mimas suggests that the solar system may host many invisible oceans, waiting to be revealed through more refined methods of detection. These oceans may have existed for hundreds of millions or even billions of years, entirely unaware of our existence. From the undeniable data returned by the Cassini spacecraft, the truth has become clear. Enceladus, Saturn's small moon, has forced science to revise its criteria for the search for life. Its water-rich plumes, laden with salts and organic compounds, provide concrete evidence that the necessary energy and chemistry can exist deep beneath an icy shell, entirely independent of a large planet or direct sunlight from the sun. This represents a profound paradigm shift. If life emerges there, it would arise in darkness, sustained solely by tidal energy and the appropriate physical and chemical conditions of a subsurface ocean. Enceladus is not merely a celestial body, it is a scientific proof of concept, showing that life may be far more widespread than we once dared to imagine. Although Enceladus cannot yet answer the ultimate question, are we alone in the universe? It has transformed that question from a philosophical hypothesis into a serious, testable scientific problem. Within its quiet yet promising hidden ocean, the universe seems to whisper of an entirely new frontier of exploration. More oxygen than today, yet breathing it could kill you. We are going back to the Carboniferous Period, one of the strangest and most mysterious chapters in Earth's history. This was the age when colossal fern forests emerged. They pumped unprecedented amounts of oxygen into the atmosphere, driving concentrations to extreme levels, possibly reaching 35%, far higher than today's 21%. This was not the cool green era often portrayed in textbooks. It was a time marked by something far more terrifying: the gigantism of insects. Imagine this: you are standing in a dense, humid forest, and above your head flies Meganura, a dragonfly, with a wingspan reaching up to 75 centimeters. Or picture Arthropleura, a giant millipede stretching as long as 2.6 meters. Now imagine a world where tropical storms strike frequently, unleashing violent floods and creating vast sprawling wetlands. How could life possibly survive in such extreme conditions? Right now, we are about to descend into the shadows of these prehistoric forests. According to geochemical studies based on fossilized coal and ancient wildfire indicators, excess oxygen did more than sustain life, it transformed life itself. In that context, the ground was no longer the domain of small creatures. It became a refuge for massive bodies that today we can only imagine as monsters. Arthropleura stands as the clearest symbol of this upheaval. It was a terrestrial arthropod, a distant relative of modern millipedes, commonly measuring 2 to 3 meters in length. With some fossil evidence suggesting individuals may have reached nearly 6 meters, close to 20 feet. To this day, Arthropleura is considered the largest land-dwelling arthropod ever to exist. What is remarkable is not only its size, but the fact that such size was not paired with sophisticated biological weapons. There was no lethal venom, no specialized biting jaws. Arthropleura existed because the environment allowed it to exist at that scale. Arthropods breathe through a tracheal system, in which oxygen diffuses directly from the air into tissues, without relying on a circulatory system like that of vertebrates. Under low or moderate oxygen conditions, this mechanism imposes strict limits on body size. When oxygen flooded the atmosphere, diffusion efficiency increased dramatically, weakening the physiological barrier that had long restrained bodily expansion. Size was no longer a survival challenge, it became an almost natural consequence. Arthropleura was not alone. Homo scorpius, an ancient scorpion species, reflects the same trend. Fossils indicate it could reach lengths of around 71 centimeters. Possessed 4 eyes and lived within humid, swampy forest ecosystems. A scorpion the size of a small child is not a product of imagination, but the result of selective pressure within a distorted environment. When resources are abundant and competition is scarce. Evolution is not forced to optimize, it merely expands. In such a world, large size became a passive advantage. Difficult to attack, capable of accessing abundant plant resources, and able to dominate ecological space without significant competition. High oxygen concentrations also greatly increase the risk of wildfires, as even a minor ignition source could trigger vast infernos. Stratigraphic studies reveal that Carboniferous wildfire traces appear with unusually high frequency, confirmed through fossilized charcoal. In this context, the hard armor and massive bodies that once gave Arthropleura an advantage became fatal weaknesses. They could not run fast, could not burrow deep, and had no survival strategy against large-scale fires. The giant creatures of the land did not collapse because they were weak, but because they were born into a world already out of balance. Arthropleura and Pulmonoscorpius existed, but they could not endure. The Carboniferous period clearly shows that when a planet allows size to exceed familiar limits, life must also bear the consequences. The land during that time was no longer a place for small, agile, or finely adapted organisms. It belongs to slow, massive bodies supported by an oxygen-rich atmosphere and an energy-surplus ecosystem. And that imbalance was not confined to the ground alone. It was quietly reshaping another realm, the sky. Where new predators would spread their wings and claim an ecosystem that was nearly empty. And it is there that the Carboniferous nightmare rises to an entirely different level. Paleontologists refer to this era as the golden age of sharks, because sharks dominated nearly every upper level of the underwater food chain. What set Carboniferous sharks apart was this: when food was abundant and stable, they did not focus on catching prey faster, but instead shifted toward exploiting prey more efficiently. This opened an entirely different evolutionary space where body shape, jaw structure, feeding mechanics, and survival strategies became the central focus. The fossil record shows that Carboniferous sharks occupied multiple ecological niches at the same time. Some hunted in shallow coastal waters, others adapted to brackish swamp environments, and some ranged far into the open ocean. The underwater food web became clearly stratified. Bottom-dwelling organisms, bony fish and small cartilaginous fish, mid-sized sharks and apex sharks at the top. Each tier was locked in by specialized survival strategies. When one link weakened, another immediately filled the gap. Yet this very dominance made Carboniferous marine ecosystems fragile in a different way. When a food chain becomes too dense and too layered, ecological flexibility declines. Species grow increasingly specialized, heavily dependent on specific food sources and narrowly defined environmental conditions. And the most unsettling part is this: sharks did not stop at familiar designs. In an energy-rich environment, evolution no longer optimized for good enough, but began experimenting with strange, even risky solutions. Unusual jaw structures, counterintuitive body shapes, and hunting strategies unlike anything that exists today began to appear. At this point, water was no longer just a place to survive. It became an uncontrolled evolutionary laboratory. Ambush predators in the darkness, where silence could kill faster than teeth or claws. Stethecanthus was an ancient shark species with an average length of about 0.9 meters, 3 feet. And an estimated mass of roughly 9 kilograms, 20 pounds. What made it stand out in the Carboniferous shark world was its highly unusual dorsal structure. A large dorsal spine combined with a thick pad of tissue, rough textured and standing upright like an overturned ironing board. There is no evidence that this structure helped it swim faster, hunt more effectively, or defend itself better against predators. Morphological and comparative anatomical studies suggest that this spine brush complex may have been linked to display behavior. Possibly serving purposes related to reproduction, deterring rivals of the same species, or communication in murky, low-light waters. This makes Stethecanthus an evolutionary anomaly that is deeply unsettling from a theoretical perspective. Stethecanthus is a vivid reminder that evolution does not always produce the most optimal organisms, but rather those capable of surviving under specific conditions. If Stethecanthus represents morphological strangeness, other Carboniferous sharks reveal boldness in biological mechanisms, especially in jaw structure. A notable example is Estes, an ancient marine predator known from fossils indicating extraordinary size. With an estimated length exceeding 6.7 meters, 22 feet. It was one of the largest predators ever to inhabit Carboniferous oceans. What made Estes remarkable was not just its size, but how its jaws functioned. Fossils show an upper jaw approximately 30.2 centimeters long, while the lower jaw reached about 43 centimeters, creating a pronounced asymmetry. The jaw joints indicate movement that was not a simple open and close motion along a single axis, but instead operated like a pair of shears with multiple phases of motion. A mechanism often described as a two-gear system. This allowed prey to be processed with extreme efficiency once restrained. Slicing, tearing, and separating tissue with remarkable force and precision. What Stethecanthus, Estes, and many other unusual Carboniferous sharks share is morphological freedom. Sharks of this era were not confined to a single standard design like modern sharks. They displayed dorsal spines, unconventional body proportions, asymmetric jaw structures, and non-repeating survival strategies. However, when evolution invests too heavily in specialized designs, ecological flexibility begins to erode. A creature optimized for processing prey in an energy-rich environment faces severe difficulty when food supplies decline or when ecosystem structures shift. Bizarre forms are often tightly bound to specific conditions. They perform well in a stable world, but become fragile in the face of change. Within dense swamp forests, where light is swallowed by thick canopies and heavy moisture hangs in the air, an entirely different form of predation emerged. This was a world of hunters that did not need to chase, did not rely on speed or sustained strength. But survived by waiting for a prey's mistake in the darkness. In such an environment, running fast for long periods was nearly impossible. Every step consumed energy and carried the risk of becoming trapped. Fossil evidence shows that many species from this period possessed bodies exceeding 30 centimeters in length. With low, compact builds and wide frames, some reaching sizes comparable to a human head. These were not bodies optimized for endurance running, but for releasing explosive force in brief moments. Analyses of limb bone structure reveal large muscle attachment sites and robust joints, allowing for sudden bursts of acceleration. Biological models based on anatomy suggest these creatures could reach short-term speeds of around 15 to 16 kilometers per hour. Not to pursue prey, but to end the hunt within the first few seconds. Carboniferous predators dug burrows or exploited tree root cavities. Mud crevices and rotting stumps as hiding places. Prey was not subjected to constant pursuit, but instead lived under persistent unseen tension, moving more slowly, behaving more cautiously, and even reproducing differently. Burrows and hiding cavities within Carboniferous swamp forests were extremely vulnerable to flooding. The hot, humid climate made heavy rainfall frequent. Flat terrain caused water levels to rise quickly but drain slowly. A sudden flood could submerge entire burrow systems within hours, turning shelters into death traps. This reveals that the most successful ambushers were also the ones facing the greatest sudden risk. There was no time to flee, no escape route. When water rose, burrows collapsed, or mud poured in. Death arrived swiftly and without discrimination. Slower individuals, Those that dug too shallow or those that chose the wrong location vanished without leaving descendants. The Carboniferous was not a world of long-term strategies. Evolution here was immediate effectiveness combined with chance. It was a world ruled by decisive moments. In confined spaces, with unstable food supplies and ecological isolation, the rivers, lakes, freshwater swamps of the Carboniferous Period became the harshest crucible of natural selection. The Canthus emerged, an ancient shark species with an average length of about 3 meters, 10 feet. Living roughly between 315 and 275 million years ago. And most importantly, it inhabited primarily freshwater environments, inland river systems, enclosed lakes, and dense swamps, where water flowed slowly, remained murky, and shifted dramatically with the seasons. Fossils of Orthocanthus have been found across multiple continents, indicating a near-global distribution during the late Carboniferous. Its body was long and slender, almost eel-like, well suited for slipping through narrow channels and flooded root systems. On its head rose a sharp dorsal spine, believed to have been venomous, allowing it to defend itself or subdue prey within confined spaces. Fossilized feces attributed to Orthocanthus have been discovered containing bones and teeth of juvenile Orthocanthus themselves. This is not speculation based on ecological modeling. It is undeniable physical evidence. Adult Orthocanthus consumed their own offspring. Not as rare anomalies, but as part of a survival strategy. Food availability depended on rainfall, flood cycles, plant decay, and benthic organisms, all of which were extremely sensitive to environmental change. A prolonged drought, a flood that wiped out bottom-dwelling life, or the accumulation of oxygen-poor sediment was enough to collapse the entire food chain. Under such conditions, juveniles became the most reliable source of energy. When the environment could no longer support an entire generation, eliminating part of the next generation allowed adults to survive and preserve their future reproductive potential. Evolution cares only about the probability of survival. This reveals a fundamental difference between freshwater systems and the oceans during the Carboniferous. In the oceans, energy surplus allowed for complex and indirect strategies. But in freshwater, every strategy had to be direct and immediate. Orthocanthus was not the fastest predator, nor the largest. But it was among the most perfectly adapted to harsh conditions. Its elongated body conserved energy while moving slowly through stagnant water. Its venomous spine allowed prey control without pursuit. And cannibalistic behavior ensured that energy did not leak out of the system. Notably, Carboniferous freshwater environments did not only produce cannibalism, they also shaped hunting strategies fundamentally different from those of the open ocean. Murky water, poor visibility, and complex terrain filled with roots, decaying logs, and thick mud made long-distance pursuit nearly impossible. From these dark waters, evolution began favoring creatures capable of ambush, concealment, and delivering decisive strikes within fleeting moments. From enclosed freshwater systems, the Carboniferous story now slides into an even more terrifying chapter. Ambushers in the darkness, where silence kills faster than teeth and claws. When we look at the Carboniferous as a whole, the truly terrifying thing is the environment that produced all of this. The Carboniferous was not merely a unique biological period. It was a rare moment in Earth's history when the entire planet functioned like a colossal swamp machine, constantly fueling life beyond normal limits, while quietly accumulating the conditions for its own collapse. Between roughly 358.9 and 298.9 million years ago, most of the continents were clustered near the equator. This distribution subjected Earth to a prolonged hot and humid climate, with high and relatively stable rainfall lasting tens of millions of years. These were not short-lived climate cycles, but a long-standing baseline state, one that endured long enough to reshape the planet's entire surface. These forests were dominated by ancient vascular plants such as giant lycopsids, horsetails, and tree ferns, ranging from several meters to over 30 meters in height. Their life cycles were fast, their biomass immense, and most critically, much of their plant matter fell into waterlogged, oxygen-poor environments. Under such conditions, decomposition slowed dramatically. Carbon was buried and accumulated as thick layers of peat, altering the balance of the atmosphere. As carbon dioxide was removed from the short-term cycle, oxygen began to build up. High oxygen levels intensified metabolic processes, relaxed the physiological limits of many groups of organisms, and removed the constraints that once restricted body size. Extinction did not occur as a single catastrophic event, but as a series of cascading breaks across ecosystems that had already been under strain. The Carboniferous, therefore, was not a golden age in any sustainable sense. It was a partially failed planetary experiment. Earth demonstrated that life can explode spectacularly when barriers are removed. But it also showed that every extreme system carries the seeds of its own destruction. Life did not collapse from a lack of energy, but from too much energy contained within an unstable structure. As the Carboniferous slowly drew to a close, the most haunting legacy was the presence of organisms that could not be neatly placed into any evolutionary drawer. The Tully monstrum, gregarium, stands as the clearest symbol of the ambiguity, uncertainty, and instability that defined the entire period. First discovered in the state of Illinois, USA, within sediment layers dated to around 307 million years ago during the late Carboniferous. It was not large. Its average length was only about 35 centimeters. But it ignited more than half a century of scientific debate. Body was soft and elongated, lacking a hard shell and lacking obvious bones. Resembling a squid more than a fish. Its eyes sat on long stalks extending sideways, allowing it to observe both directions at once. At the front was a long proboscis ending in a jaw armed with 16 teeth, resembling a biological pincer more than the mouth of any familiar animal. It does not fit cleanly among invertebrates. Yet it also fails to align with any known group of vertebrates. However, some specimens show traces of characteristic proteins associated with cartilage. Suggesting that the Tully monster may belong to a primitive vertebrate lineage. In addition, structures interpreted as gills, along with signs of a rudimentary spinal cord, further support this hypothesis. There is no clear evidence of a lateral line, the water vibration sensing system, that is almost mandatory in fish. No structures corresponding to balance organs such as an inner ear have been identified. Its body plan also fails to match any known evolutionary branches of fish. The result is that the Tully monster stands at the edge of every classification system, belonging fully to none. The existence of such a creature is a direct product of an uncontrolled evolutionary environment. It demonstrates that evolution does not always produce clear, continuous, or logical lineages. The Carboniferous ended, but its lesson remains. When a planet pushes its systems beyond the threshold of balance, life does not choose safety or morality. It exploits, expands, and experiments until the very foundation of existence can no longer support it. And so, when we look back at the Carboniferous, the question is not what survived, but what was lost when Earth transformed itself into a world unfit for stable life. Earth was once a true nightmare, and the Carboniferous stands as a reminder that such nightmares require no intelligence, only the right conditions to emerge. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond. The universe, a vast and mysterious expanse, not only houses our solar system, but is also home to billions of other planets. Each one a unique, untold story waiting to be discovered. Among these worlds, could there be one like Earth, where life might take root? With the advancement of technology, following the success of Kepler, the TESS telescope was launched in 2018. With its ability to survey 85% of the sky and focus on nearby bright stars, it has ushered in a new era of searching for planets with Earth-like conditions. TOI 700D, a planet similar in size to Earth and located within the habitable zone of a red dwarf star, could be a strong contender for supporting life. Meanwhile, the planet Teegarden B, with the highest Earth similarity index, is sparking curiosity among scientists about the adaptability of life under extreme conditions. However, not all exoplanets promise life. Some planets, like TESS 2b and 55 Cancri E, possess extreme conditions that render them into what could be described as death planets. Now, let's embark on a journey to uncover the fascinating secrets of these exoplanets. The first and most essential tool in shaping our understanding of distant planets is Kepler. Launched into orbit on March 7, 2009, Kepler was not just a telescope. It was a massive light-measuring machine designed to observe a single section of the sky continuously for nearly a decade. This method relies on a highly refined physical principle. When a planet passes in front of its parent star, it dims the star's light by a fraction, sometimes as little as 0.01%, equivalent to detecting an ant crossing a car's headlights from a distance of 100 meters. Kepler proved that small, Earth-like rocky planets were not anomalies, but rather the rule across the galaxy. With more than 2,600 confirmed planets, Kepler accomplished its mission, providing undeniable statistical evidence of the commonality of other worlds. We found them, but what exactly are they made of? If Kepler was the hunter searching for numbers. The Transiting Exoplanet Survey satellite, launched on April 18, 2018, took a different approach. TESS doesn't aim to look far. Instead, it focuses on nearby. Bright stars and surveys a wide swath of sky. As of now, TESS has confirmed over 390 exoplanets and created a list of over 6,600 potential candidates. Notably, TESS discovered the TRAPPIST-1 system, shifting the scientific focus from simply proving existence to searching for signs of life. Chemical traces in atmospheres by concentrating on brighter, nearer stars within just 200 light years